Hi everyone, in this video we're going to continue talking about polynomial long division, the division algorithm, and I'm also going to tell you about a useful theorem called the remainder theorem. So let's first begin by computing another example of polynomial long division. I want to divide this degree 2 polynomial, this quadratic, by this linear polynomial, x plus 3. So I set it up just like I set up normal long division. I put the thing I'm dividing by on the outside, and the thing I'm dividing into on the inside of this bar. Now I will look at the first part and see how many times that goes into the second part. So or the first part of the inside. So what I put here is the number of times x goes into x squared. So what times x equals x squared? That's x. Now I take x, I multiply it by this entire expression, and I put that below, just like I do in long division of real numbers. X times x is x squared, x times 3 is 3x. And just like long division of real numbers, I subtract this away. So it's really important to put this in parentheses so you remember to subtract both terms. X squared minus x squared is 0. 5x minus 3x is 2x. And I bring down the 12. Now I repeat the process with this polynomial. So I want to know how many times does x go into 2x, and I put that here. So this is the number of times x goes into 2x. Or in other words, what do I have to multiply x by to get 2x? Well, that's easy. That's just 2. X plus 2, or 2 equals 2x. So now I take this 2, I multiply it by this entire expression, and I bring it down. So the same process, just repeated again. So 2 times x plus 3 is 2x plus 6, and again I have to subtract this entire expression. 2x minus 2x is 0, 12 minus 6 is 6. So what I found here is that x squared plus 5x plus 12 divided by x plus 3 is equal to x plus 2 with a remainder of 6. According to, if we were to rephrase this, what it says is that x plus 2 times x plus 3 is almost x squared plus 5x plus 12, but we have to add 6. So let's see why that's true. If I do x plus 2 times x plus 3 alone, I get x squared plus 3x plus 2x plus 6 just by FOIL. That's x squared plus 5x plus 6. So in order to get the polynomial I want, I need to add the remainder. So this tells us that x plus 2 times x plus 3 plus 6 equals the thing we started with. This is the division algorithm. Here's the thing we started with. It equals the thing we're dividing by, so that's what we called p of x before. It equals the thing we're dividing by, which is d of x, times the quotient, which was x plus 2, plus a remainder. And the remainder has smaller degree than what we started with. Sorry, this was hidden before. If I add 6 onto that, I get the polynomial I wanted. So here's another thing that's similar to what we did with long division of real numbers. If I do x squared plus 5x plus 6, and I do my long division, it's not really going to fit here, but maybe we can do it quickly. And I divide that by x plus 3, x goes into x times. X times this expression is x squared plus 3x. And I subtract it, so I get 2x plus 6. x goes into 2x 2 times. 2 times x plus 3 is 2x plus 6, and I get 0. Again, remainder 0, let's hide this. Remainder 0 means x plus 3 is a factor. In other words, I could write x squared plus 5x plus 6 as x plus 2 times x plus 3. And you could check that yourself just by factoring this expression. You don't actually need long division. We'll come back to this relationship between factors and remainder 0 in the next video. So here is another example that I want to work out with you. Although maybe we should do the remainder theorem first. So we'll come back to that. All right, so remainder theorem. What this says is for a polynomial p of x, you can evaluate p of c by dividing p of x by x minus c. And so the result is the remainder of this division is going to be equal to p of c. So for a proof of this, the idea, I'm not going to give it to you, but I'll give you extra credit if you do it yourself. But the idea is that you want to use the division algorithm to write p of x as x minus c times whatever you get for your quotient plus a remainder, and then plug in c. Because then on this side you'll have p of c, and on this side you should end up getting just a remainder if you do it correctly. So you want to plug in c to both sides for x. That proof, I'll give you extra credit if you show it to me. So let's do an example where we actually use this division algorithm. So here's my polynomial, x cubed minus 10x squared plus 21x minus 12. And I want to use the remainder theorem to find p of 2. So again, the remainder theorem says I divide by x minus c. So in this case, c is 2. So I'm going to divide by x minus 2 and look at the remainder. So I take x minus 2 and I divide it into x cubed minus 10x squared plus 21x minus 12. So this is a much longer expression, so we'll just repeat the process over and over and over again. So first I look to see how many times does x go into x cubed. That's x squared. I take x squared, I multiply by this expression, and I put it below. X squared times x is x cubed, and then I get minus 4x squared, or sorry, 2x squared. And I'm going to subtract this entire expression. So I'm left with negative 10x squared minus negative 2x squared is negative 8x squared. And I bring down this other stuff and repeat the process, except I look to see how many times does x go into negative 8x squared. That's going to be negative 8x. I take this, I multiply it by that expression, and I put it below. So I get negative 8x squared minus 16x. And then I'm going to subtract this entire thing from the expression above. So here, these cancel. 21x minus negative oh, this was plus 16x, so 21x minus 16x is 5x. And then I bring down the minus 12, and I repeat the process again. How many times does x go into 5x? That's just 5. 5 times x minus 2 is 5x minus 10, and I need to subtract this, and I'm left with negative 2. So the remainder is negative 2, which means that by the remainder theorem, f, or p of 2 equals negative 2. And we can check this by plugging in. So if I do p of 2, I'm doing 2 cubed minus 10 times 2 squared plus 21 times 2 minus 12. 2 cubed is 8. This next term is minus 40 plus 42 minus 12. And if you check this arithmetic, that actually does equal negative 2, so it works. So those are the nuts and bolts of the remainder theorem. In order to get you thinking about the next theorem that we're going to hit in the next video, think about what it would mean if the remainder was 0. So if we got a remainder, so say we did this and we got a remainder of 0, that would say that p of 2 equals 0. So that's p of, if r equals 0, that says p of 2 equals 0 by the theorem. So what does that say about 2? This is where we're going in the next video. So think about that, and then we'll talk about zeros and roots some more.